the first stage, okay, suppose I take a beaker which is filled with a fluid, okay, and so there will be a certain temperature range. Till that temperature, the process that occurs is only by, the heat transport is only by natural convection. And in fact, if I start to develop this boiling curve, okay, so there is a certain region till which point the primary mode of heat transport or the dominant mode of heat transport is the natural convection. And what happens is, supposing I supply heat here and this is the temperature of the surface. So what happens is there will be occasional bubbles which will be formed, okay, sporadic bubbles will be formed at the bottom surface, and because of the density difference they will start moving up, and this will set up the recirculation motion in this container, and so that causes the natural convection. So the primary, I should say the dominant mode of heat transport here is simply by convection, natural convection, because of displacement of the fluid. Okay. Still the maximum contact of the surface to the fluid is still the liquid phase. There will be sporadic bubbles which will be formed. So the primary transport of heat is only between the solid surface and the liquid surface. I mean the liquid which is in contact with the surface. Okay. So this is what is called the natural convection mode of boiling. And then the second one, okay, is called the nucleate boiling. Okay. Nucleate boiling actually has two regions. So the free convection is till this point. So all the way up to the maximum. Okay. So if I call this as some maxima C, okay, and this is again delta T versus the flux of heat that is supplied for boiling. So what happens is, so this is the fluid and I have a heating system below. So what happens is, till a certain point, so there will be an inflection point on this curve, okay. So till the inflection point, you will see that there will be significant bubbling of this vapors which will come here. So the bottom surface will now have significant amount of bubbles, and so there will be significant bubbling. So now the heat transport is not just by the free convection, because there is a good fraction of the bottom surface which is in contact with the vapor bubble. So therefore the heat transport is going to be both because of the sensible heat which is carried by the vapor and the sensible heat which is carried by the liquid phase of the same fluid. So now the phase change has affected heat transport by both liquid and the vapor phases. Now what is the nature of the conductivity of vapor phase compared to liquid? It's always lower, right? So the conductivity of the vapor phase is always lower than the conductivity of the liquid. So what happens is that till the inflection point, still the majority of the energy is carried by the liquid phase, and therefore what you will observe is that the heat transport coefficient will continue to increase all the way up to the inflection point, till the situation where they have a switch in the extent of heat that is transported by the liquid or the vapor phase. Okay. So that's the third stage. So that's the third stage of boiling, where it's still nucleate boiling, because it's still the mechanism is nucleation. Nucleate boiling is that there will be significant vapor formation, bubble formation at the bottom surface, and some of these bubbles, because they are formed so close to each other, they are going to coalesce with each other and they will form what is called the vapor stream. So, these are the vapor streams. So, you will start seeing vapor streams which is going together. So, a channel of vapor is created, and so the heat transport is now because of the heat that is carried by the vapor phase. So, there will be a change in the dominant mode of heat transport. So, I should say that heat transport is now primarily due to heat carried by the vapor. Okay. So, the heat is primarily carried by the vapors because the density of the vapor phase is significantly smaller, and so the coalescence will occur very quickly and they also move very quickly. So, this is actually going to increase the recirculation in the fluid in this chamber, and so there will be vigorous mixing that will be introduced. So, the mixing is introduced in this particular stage. Now, what happens is because the conductivity of the vapor is much smaller than the conductivity of the liquid, okay, so the net amount of heat that is transported, remember the net amount of heat that is transported is going to reduce. Okay. So, therefore, you expect that the heat transport coefficient H will start decreasing with the more vapor that is formed, and the reason behind is that the vapor which is formed is immediately transported out, and so they are not in complete contact with the bottom surface. So, the residence time for the vapor phase near the surface is very small, and so the contact time is small and also the conductivity is very small. So, therefore, the heat transport coefficient will start decreasing as soon as you reach the third stage, okay. And the boiling curve here is, so if I put, so that stage is all the way up to the maximum, okay. And what happens after that is called the transition stage, okay, where you cannot distinguish whether the bottom surface is now in contact only with the fluid or only with the vapor phase. It is going to be a constant switch between the vapor and the liquid phase. So, therefore, the heat transport coefficient will continue to decrease because it is constantly switching, and so the residence time or the contact time between the fluid and the solid is going to be significantly smaller. Okay, so, the transition stage also the heat transport coefficient will continue to decrease. So, that is the transition stages from the maxima to the minima. So, this is the transition stage, okay. And the last stage is the called the film boiling. Now, at this stage there is sufficient amount of heat that has been provided. So, the bottom of the container is now going to be filled with a vapor film. So, the temperature difference is significantly higher, that any fluid which comes in contact with the bottom surface is going to be instantaneously converted into its vapor state. So, the bottom surface will always be in contact with the vapor phase of the fluid, and so the primary heat transport is because of the conductivity of the vapor phase. Okay. So, the vapor will form and they will all escape out. Okay. So, that is the mechanism, and so the boiling curve at that stage would be so now as you further increase the heat that is provided, so you increase the temperature difference, this is Ts minus Tsat, and therefore the net amount of flux of heat that is carried is going to increase with increase in the temperature difference. So, this bottom minima is called the, just for historical purposes, it's called the Leidenfrost point. Okay. So, although it seems so obvious for us when we see heating of water or boiling of water that suddenly the vapor phase is formed, it's actually not that trivial. If you actually observe it very closely, you will see these vigorous mixing, you can see that, and it's very easy to see this. So, next time when you go to your hostel, when there's water boiling, I don't know if you are permitted in the kitchen, but let's say if you are permitted, you can actually see boiling of water. You will see that initially you will see these small bubbles which will come, and they will slowly they will come to the surface, they will burst and they will go. And then after a while, when you continue to supply heat furthermore, you will see that there will be vigorous vapors which are formed, and you will see these big bubbles which will come to the surface and they will start bursting. So, the top surface will not be flat anymore, you will see there is a lot of vigorous vapors coming in and going out. Okay. So, that is actually the second stage or third stage, which is nucleate boiling, where there is vigorous vapor which is formed, and film boiling is the stage where you will see that most of the fluid is already gone. They have already been converted into vapor, there is just very little fluid left, and so the bottom will now be filled with vapors. So, usually you never want to reach this stage. Most of the times when you heat water, you never want to reach this stage of having a film at the bottom, because the film temperature difference can be significantly higher. It is not the most favorable condition. So, you never want to reach this stage. So, you never touch the Leidenfrost point. So, what is typically done is that once the fluid reaches this maximum, okay, so the best way to boil a fluid is you slowly go and reach the maximum on the boiling curve, and then you maintain a constant flux condition. You maintain a constant flux and you reach here. So, this is a constant flux. So, you provide constant flux of heat and then you go and reach the other end of this curve, and that is how you ensure that most of the things is boiled. You never want to reach the Leidenfrost point because it is too much waste of energy. Okay. Oh, okay. So, what happens is that in supposing I look at, this is the beaker. Okay. Now, what happens is here, suppose let us say there is fluid which is present in this location and there is vapor bubble which is present here. So, now you can have a similar situation, you have vapor, liquid, vapor, liquid. Now, in transition region, the temperature difference between the surface and the saturation or the boiling point temperature is so high that whatever fluid that comes here is now going to be almost instantaneously converted into vapor phase. But it is still not significantly higher that at every location it will be converted into a vapor phase. So, therefore, as soon as the vapors are formed, the vapors are now transported out from that location. So, therefore, what happens is that the contact time that this liquid or the vapor that has with the surface is going to be significantly lower. So, therefore, the amount of heat that is transported in this regime is not going to be that significant, and that is why the heat transport coefficient actually goes down. So, remember that heat transport coefficient is only a representative number, it is a fictitious quantity. It is a representative number which tells you what is the extent of heat that is transported. So, the extent of heat that is transported here is not significant because there is a constant exchange of fluid and vapor at the surface where the fluid is being heated. and that is why the heat transport coefficient actually goes down significantly. I'll draw in a minute how the heat transport coefficient profile will look like. So the flux of heat transport, okay, so that should be heat transport coefficient multiplied by delta T, right. So now if I draw the Qs versus delta T, okay, so I basically have this behavior, right. So now what happens is that, so H is actually can actually be directly calculated from the boiling curve. So if I plot the H versus delta T, okay, so what happens is that till the inflection point, if I call this as B, okay, till the inflection point, the heat transport coefficient will continue to increase, and the physical mechanism is that the liquid is still, the primarily liquid is in contact with the surface, which has a higher conductivity, and therefore it is enabling higher heat transport till that location. But then moment it touches the inflection point, the offset in terms of the contact that you will have with the surface is significantly higher compared to the offset that you will get by increasing the delta T. So remember that Qs is now a function of both heat transport coefficient and the temperature difference. So supposing if I want to, so I increase the flux here, okay. Now increase in the flux here is because of the increase in the delta T and not because of the increase in the heat transport coefficient. So now there is a competition between, so if I now look at the flux, now the increase in the flux is because of competition between increase in the temperature difference versus the decrease in the heat transport coefficient, and the decrease is because the contact is not completely fluid, it is not completely vapor, so there is going to be a mixture of both, and so the net effect is that the extent of heat transport is going to reduce, and therefore what you will see is that at the inflection point you reach a location where there is a maximal heat transport coefficient, and the heat transport coefficient will start decreasing. So this location is now C, I put C as the maxima point, okay. So it is not able to withstand the decrease in the heat transport coefficient. So heat transport coefficient will now at this location C, it will decrease significantly lower, and so any increase in delta T is not going to lead to increase in the flux of heat transport, okay. So therefore till the Leidenfrost point, so if I call this as point D, so till the Leidenfrost point where the bottom is now completely covered with a vapor film, the heat transport coefficient will continue to decrease, and after that it is a single phase system, because the bottom, whatever fluid that comes to the bottom is instantaneously converted to the vapor phase. So there will be a film of vapor which is always present on top of the bottom surface. So therefore it is now a single phase heat transport process. So therefore the heat transport is simply going to increase as you increase the temperature difference. There is no multiple phases here. There is phase change, but there is no multiple phases that is in contact with the bottom surface of the container which is now heating the fluid. So this is the kind of heat transfer coefficient profile that you will get. See, if you want to maintain the bottom surface constant, okay, now you provide heat to the bottom surface. Now you have to ensure that all the heat that is given to the bottom surface is now transported to the fluid. That does not happen because you have multiple phases here. You cannot control that. You have multiple phases. You have change in the phases now. So you cannot keep delta T constant anymore. So that is a problem. Until all the fluid is now heated and converted into vapor phase, the fluid will continue to be at Tsat temperature. Only the vapor temperature, the local vapor temperature will go above Tsat, but they are going to escape and go away. So the liquid is still continue to be in Tsat temperature. They will continue to be at the boiling point till all the liquid is escaping into vapor phase. Okay. Okay, so what we are going to do in the next 5 minutes or so is, so there is no way to get, first of all, there is not easy to write the governing equations, and therefore there is no way to get analytical solutions. So there are some correlations which are available. So if you take free convection case, that is stage 1. We have already looked at some of these correlations. So you have to use the correlations developed in, we already know them because we already looked at natural convection problem. So the second stage is where you have nucleate boiling. You have nucleate boiling. So there is something called Rosanoff correlation. Okay. So now this correlation essentially gives you what is the maximum flux, what's the maximum point, because that's what is important for from operation point of view. Remember I drew this curve where if you want to heat the fluid, moment you touch the maxima, you would like to maintain a constant flux condition. So it's important to predict what is the maxima at which the boiling curve is going to reach. So that's given by mu L multiplied by rho V divided by sigma to the power of half multiplied by Cp okay. So the Cp delta T by Hf, what is that? We saw this dimensionless quantities, right? That's the Jacob number. So this is that's the Jacob number, okay. And what about bond number? Where is bond number in this expression? It's here. So some form is here. So you can reformulate it into bond number. So really the dimensionless quantities are actually present here. In fact, that's how this expression was derived. So in order to know what should be the functional form, you need to know what these dimensionless groups are. Okay. Alright, so then so in the film boiling case, the Nusselt number, which is, so assuming that it's a cylindrical beaker, that should be, that's given by C into G rho L rho V G mu V V sat to the power of 1 by 4. So that's the correlation for Nusselt number at the film boiling case. So Hf, I have put a prime here. The reason I have put a prime is depending upon the temperature difference. So it could be either just the conduction mode of heat transport at the boundary, or you could also have a radiation mode of heat transport. Okay. So suppose if you have radiation mode of heat transport also, then the overall heat transport coefficient that you get, which is H bar, is related as H bar 4 by 3 convection plus H bar radiation into H bar to the power of 4 by 3. Okay. So note that it's not linear. So H bar radiation is defined as epsilon sigma Ts to the power of 4 Tsat to the power of 4 divided by Ts minus Tsat. So it's very similar to the way we defined. So remember, this comes from the flux equal to some H into delta T. So use that definition to define heat transport coefficient because of radiation. Okay. So epsilon sigma is Stephen-Boltzmann constant, not surface tension. okay, sigma is Stephen-Boltzmann constant. So, this is the net radiation exchange between the bottom surface and the fluid which is actually present above the film. Remember that in the film boiling case, we will have there is a film which is present, and so there could be radiation exchange between the bottom surface and the water which is present just above the vapor phase. Okay. So, that radiation exchange is given by epsilon is the emissivity multiplied by sigma into Ts power 4 minus Tsat to the power of 4. So, if you know these quantities, you should be able to calculate the heat transport coefficient.